In this lesson, we'll learn about overflow. Overflow happens when the result of a calculation is too large to fit into the available number of bits. Here, we have an 8-bit register. The register is already full, with 8 bits. But after a calculation, the answer needs one extra bit. That extra bit cannot be stored because the register has reached its limit. This is called overflow. Computers use fixed-size registers and memory. When calculations produce numbers larger than the available space, the processor detects an overflow, and the stored result may become incorrect. In this lesson, we'll see why overflow happens, how to identify it, and how computers handle it. Let's see what happens when a number doesn't fit. This is a 4-bit register. The largest value it can store is 1111, which is 15 in decimal. Now, we add 1. The correct binary answer is 10,000. But notice, 10,000 needs 5 bits. Our register only has 4 bits. The first 4 bits can be stored, but the extra bit on the left has nowhere to go. When the result is larger than the available number of bits, overflow occurs. This is why computers have limits based on the number of bits they use. Now, let's define overflow. Overflow happens when the result of a calculation is too large to be stored using the available number of bits. Here's an example. Using 4 bits, we add 1111 and 0001. The correct answer is 10,000. But notice, the register has room for only 4 bits. The first 4 bits fit inside the register. However, the extra bit on the left cannot be stored. That means overflow has occurred. Remember, the largest unsigned value in a 4-bit register is 1111 or 15. Adding 1 produces 10,000, which is 16. Because 16 needs 5 bits, it cannot fit into a 4-bit register, so the calculation results in overflow. Computers use a fixed number of bits to store data. A register has a fixed size. It contains a specific number of bit positions. For example, a 4-bit register has 4 positions. An 8-bit register has 8 positions. And a 16-bit register has 16 positions. Each position can store only 0 or 1. The important point is, a register can store only the number of bits it was designed for. It cannot create extra bit positions when a calculation becomes larger. If a result needs more bits than the register has, the extra bits cannot be stored, and that leads to overflow. A 4-bit register has limits. It can store binary numbers starting from 00000 up to 1111. That means it can represent decimal values from 0 to 15. With 4 bits, there are 16 possible combinations because 2 to the power of 4 equals 16. Now look at the number 10,000. This pattern requires 5 bits, but a 4-bit register has only 4 positions. So, 10,000 cannot be stored in a 4-bit register. The key point is, a 4-bit register can store values only from 0000 to 1111. Anything larger, like 10,000 or 16 in decimal, needs more than 4 bits. Every unsigned binary number has a maximum value. We can calculate it using the formula 2 to the power of n minus 1. Here, n is the number of bits. Let's look at some examples. With 3 bits, the largest value is 7. With 4 bits, it's 15. With 5 bits, it's 31. With 8 bits, the maximum value is 255. And with 16 bits, the maximum value is 65,535. For example, an 8-bit number with all bits set to 1 is 11,111,111. Using the formula 2 to the power of 8 minus 1 equals 255. So an unsigned 8-bit register can store values from 0 to 255. Remember, as the number of bits increases, the range of values also increases. Now let's understand why overflow happens. Computers use a fixed number of bits to store numbers. For example, a 4-bit register has only 4 bit positions. That means it can store only 16 different patterns from 0000 to 1111. Now imagine a calculation produces the value 18. In binary, 18 is 10,010. Notice this answer requires 5 bits, but the register has room for only 4 bits. Since the result is outside the available range, it cannot be stored correctly. This is called overflow. Think of it like a container that can hold only 4 balls. If you try to add a 5th ball, it simply won't fit. Binary registers work in exactly the same way. When the answer is larger than the available space, overflow occurs. Let's look at an example where overflow does not occur. We are adding 1010 and 0101. Starting from the rightmost bit, we add each column one by one. The final answer is 1111. Now let's check the decimal values. 1010 is 10, 0101 is 5, and 10 plus 5 equals 15. In binary, 15 is 1111. Notice, the answer still fits inside 4 bits. No extra bit is produced on the left. All the carries stay within the 4-bit register, so the result fits completely inside the available space. Therefore, no overflow occurs. Now, let's look at an example where overflow occurs. We are adding 1100 and 0110. Starting from the rightmost bit, we add each column one at a time. The correct binary answer is 10,010. Now let's check the decimal values. 1100 is 12, 0110 is 6, and 12 plus 6 equals 18. Notice the result 10,010 needs 5 bits, but our register has room for only 4 bits. The extra one on the left cannot be stored. That extra bit is called the overflow bit because the answer requires more bits than are available. Overflow occurs. Always remember, if the result needs an extra bit beyond the register size, the calculation has overflowed. Let's look at another example of overflow. This time, we add 1111 and 0001. Starting from the rightmost bit, we add each column step by step. The correct binary answer is 10,000. Now let's check the decimal values. 1111 is 15, 0001 is 1, and 15 plus 1 equals 16. In binary, 16 is 10,000. Notice, the answer now requires 5 bits, but the register has room for only 4 bits. Only the rightmost 4 bits can be stored. The extra one, on the left, cannot fit inside the register. This means overflow has occurred. Remember, for an unsigned 4-bit number, the maximum value is 15. Any result greater than 15 will cause overflow. Let's summarize the overflow rules. Overflow happens when the result of a binary addition is larger than the maximum value that can be stored using the available number of bits. For an unsigned number, the maximum value is calculated using 2 to the power of n minus 1. If the result stays within this limit, there is no overflow. But if the result needs an extra bit, overflow occurs. One way to detect overflow is by checking for a carryout from the most significant bit. To avoid overflow, computers can use larger data types or more bits for storing the result. Think of it like filling a container. When the container is already full, adding one more item causes it to overflow. Remember this simple rule. If the result is greater than 2 to the power of n minus 1, overflow occurs. Let's bring together everything we've learned about overflow detection. In unsigned binary addition, overflow happens when the result is greater than the maximum value that can be stored using the available number of bits. Remember, for n bits, the maximum value is 2 to the power of n minus 1. For example, a 4-bit unsigned number can store values from 0 to 15. If the result is 15 or less, there is no overflow. But if the result becomes 16 or more, overflow occurs. Another way to detect overflow is by checking the carryout from the most significant bit. If a carry leaves the leftmost bit, the answer no longer fits inside the register. To prevent overflow, computers may use larger data types or registers with more bits. Think of it like filling a small container. Once it's full, adding one more item causes it to overflow. So remember this simple rule. If the result is greater than 2 to the power of n minus 1, overflow occurs. Let's look at another example of overflow. This time, we are adding 9 and 8. First, convert them to binary. 9 becomes 1001, and 8 becomes 1000. Now add them together, starting from the rightmost bit. The correct binary answer is 10,001. Let's verify using decimal numbers. 9 plus 8 equals 17, and 17 in binary is 10,001. Notice, this answer requires 5 bits, but our register has room for only 4 bits. Only the rightmost 4 bits can be stored. The extra one, on the left, cannot fit inside the register. That extra bit indicates overflow. Remember, a 4-bit unsigned register can store values only up to 15. Since 17 is greater than 15, overflow occurs. Let's work through another example of overflow. This time, we are adding 7 and 12. First, convert them to binary. 7 becomes 0111, and 12 becomes 1100. Now, add the two binary numbers, starting from the rightmost bit. The correct answer is 10,011. Let's verify it in decimal. 7 plus 12 equals 19, and 19 in binary is 10,011. Notice the answer needs 5 bits, but our register has space for only 4 bits. Only the rightmost 4 bits can be stored. The extra one, on the left, cannot fit inside the register. That extra bit means overflow has occurred. Remember, a 4-bit unsigned register can store values only from 0 to 15. Since 19 is greater than 15, overflow occurs. Let's look at one more example of overflow. This time, we are adding 15 and 1. First, convert them to binary. 15 is 1111, and 1 is 0001. Now, add the numbers, starting from the rightmost bit. The correct binary answer is 10,000. Let's check the decimal values. 15 plus 1 equals 16, and 16 in binary is 10,000. Notice, the result needs 5 bits, but our register has room for only 4 bits. Only the last 4 bits can be stored. The extra one, on the left, cannot fit inside the register. That extra bit is called the carryout, and it indicates overflow. Remember, the largest value a 4-bit unsigned register can store is 15, so adding 1 to the maximum value immediately causes overflow. Let's go through another overflow example. This time, we are adding 8 and 9. First, convert both numbers to binary. 8 becomes 1,000, and 9 becomes 1,001. Now, add them together, starting from the rightmost bit. The correct binary result is 10,001. Let's verify using decimal numbers. 8 plus 9 equals 17, and 17 in binary is 10,001. Notice, the answer requires 5 bits, but our register has space for only 4 bits. Only the rightmost 4 bits can be stored. The extra one, on the left, cannot fit inside the register. This extra bit is the carryout, and it tells us that overflow has occurred. Remember, a 4-bit unsigned register can store values only up to 15. Since 17 is greater than 15, overflow occurs. Let's look at another example of overflow. This time, we are adding 7 and 10. First, convert both numbers to binary. 7 becomes 0111, and 10 becomes 1010. Now, add the binary numbers, starting from the rightmost bit. The correct binary result is 10,001. Let's check the decimal values. 7 plus 10 equals 17, and 17 in binary is 10,001. Notice, the answer requires 5 bits, but the register has room for only 4 bits. Only the rightmost 4 bits can be stored. The extra one, on the left, cannot fit inside the register. This extra bit is called the carryout, and it indicates overflow. Remember, a 4-bit unsigned register can store values only from 0 to 15. Since 17 is greater than 15, overflow occurs. Let's look at our final example of overflow. This time, we are adding 14 and 9. First, convert both numbers to binary. 14 becomes 1110, and 9 becomes 1001. Now, add the binary numbers, starting from the rightmost bit. The correct binary answer is 10,111. Let's verify using decimal values. 14 plus 9 equals 23, and 23 in binary is 10,111. Notice, the result requires 5 bits, but the register has room for only 4 bits. Only the rightmost 4 bits can be stored. The extra one, On the left, cannot fit inside the register. That extra bit is the carryout, and it tells us that overflow has occurred. Remember, a 4-bit unsigned register can store values only up to 15. Since 23 is greater than 15, overflow occurs.